Preparing for a big data or Apache Spark interview. This video covers the top 15 most asked Apache Spark interview questions, explained clearly with sample answers. Whether you're aiming for a role as a data engineer, big data developer, or Spark specialist, these questions will help you boost your confidence and stand out. Topics covered are core Spark concepts, RDDs versus data frames, transformations versus actions, Spark optimizations, partitioning, and more. Don't forget to like, share, and subscribe for more data engineering content. Let's get started. Question 1. What is Apache Spark? Apache Spark is an open-source distributed computing system that provides an interface for programming entire clusters with implicit data parallelism and fault tolerance. It's widely used for big data processing and analytics due to its speed and in-memory computation capabilities. Question 2. What are the main components of Apache Spark? Spark Core, Base Engine. Spark SQL, Query Structured Data. Spark Streaming, Handle Real-Time Data. mlib, Machine Learning Library. GraphX, for Graph Processing. Question 3. Difference between RDD, data frame, and dataset? RDD are the low-level, resilient, immutable, distributed collection. Data frame are distributed collection of data organized into named columns. Dataset is type-safe version of data frame, available in Scala and Java. Question 4. What is lazy evaluation in Spark? Spark doesn't compute transformations immediately. Instead, it builds a DAG, directed acyclic graph, and only executes transformations when an action is called, improving optimization. Operations are divided into two types. 1. Transformations, operations that define a new dataset, example, map, filter, join. They aren't executed immediately. 2. Actions, operations that return a result to the driver program or write to storage, example, count, collect, save. It trigger the actual computation. Question 5. What is lineage in Spark? Lineage refers to the history of operations that created an RDD. It helps Spark to recompute lost data upon node failures using DAGs. When an action, like collect, count, or save, is called, Spark uses this lineage to reconstruct lost partitions in case of failures, rather than replicating data. Question 6. What is the difference between narrow and wide transformations? Spark transformations are classified into two categories based on their data dependency patterns, narrow transformations and wide transformations. This distinction is crucial for understanding Spark's performance characteristics and fault tolerance mechanisms. Narrow, no shuffling, data stays on the same node, example, map, filter. Its key characteristics are no data shuffling, faster execution, better performance, and fault recovery is efficient. Wide, requires shuffling across nodes, example, reduceByKey, groupByKey. Its key characteristics are requires data shuffling, more expensive, slower execution, and fault recovery is more costly. Question 7. Explain Spark's Catalyst Optimizer. It's an extensible query optimization framework in Spark SQL that helps optimize queries via rule-based and cost-based optimizations. Advantages are performance boost, automatic optimization where no manual tuning needed, flexibility, and tungsten integration. Some key optimizations performed by Catalyst are 1. Predicate pushdown. 2. Constant folding. 3. Column pruning. 4. Join reordering, cost-based join optimization. 5. Partition pruning. 6. Null propagation. Question 8. How does Spark handle failures? Spark uses RDD lineage to recompute lost data, ensuring fault tolerance. It can also use checkpointing for complex DAGs. This lineage-based approach is complemented by a multi-layered recovery system where the DAG scheduler automatically retries failed tasks up to 4 times by default, while only recomputing the specific failed portions rather than restarting entire jobs. For executor failures, Spark integrates with cluster managers like Yarn or Kubernetes to automatically detect lost executors through heartbeat mechanisms and relaunch them, with tasks being rescheduled on available resources. Question 9. What is partitioning in Spark? Partitioning in Spark is a fundamental concept that determines how data is physically distributed across a cluster to enable efficient parallel processing. When a dataset is loaded into Spark, it's automatically split into partitions, smaller, manageable chunks of data that can be processed independently by different executor cores. The number and distribution of these partitions directly impact performance, as each partition is processed as a separate task in parallel. Spark offers two main types of partitioning: default partitioning, where data is split based on the input format and cluster configuration, and custom partitioning, where developers can explicitly control data distribution using operations like repartition or coalesce. Proper partitioning is crucial for optimizing operations, particularly for shuffles in wide transformations like joins and aggregations, as it minimizes data movement across the network. Key partitioning strategies include range partitioning for ordered data, hash partitioning for even distribution, and custom partitioners for specialized use cases. Effective partitioning ensures balanced workloads across executors, prevents data skew, and maximizes resource utilization, making it a critical consideration for performance tuning in Spark applications. The ideal partition size typically ranges between 100 MB to 200 MB, balancing the overhead of task scheduling with the benefits of parallelism. Question 10. Difference between cache and persist? The key difference between cache and persist in Spark lies in their flexibility and storage levels, while both serve the same fundamental purpose of optimizing performance by storing intermediate computation results in memory or disk. The cache method is essentially a simplified version of persist that defaults to storing data in memory-only storage level, making it convenient for quick optimization when memory is sufficient. In contrast, persist offers more granular control by allowing developers to explicitly specify different storage levels, like memory_AND_disk, disk_ONLY, or memory_ONLY_SER, through the storage level class, making it adaptable to various memory constraints and use cases. While both methods leverage Spark's lazy evaluation by only materializing the data when an action is triggered, persist provides the flexibility to handle scenarios where datasets are too large for memory by spilling over to disk. This makes persist particularly valuable for production environments where resource utilization needs fine-tuning, whereas cache serves well for simpler cases where memory storage is adequate and coding convenience is prioritized. Under the hood, both methods rely on Spark's resilient distributed dataset (RDD) lineage for fault tolerance, ensuring recomputation occurs if cached partitions are lost. Question 11. What is a broadcast variable? A broadcast variable in Spark is an efficient mechanism for sharing large, read-only variables across all worker nodes in a cluster, eliminating the need for redundant data transfers during operations. When a variable is broadcasted, Spark sends it to each executor just once, where it is cached and reused in subsequent tasks, rather than being shipped with each individual task. This significantly reduces network overhead and memory usage, particularly in operations like joins where one dataset is small enough to fit in memory, such as when combining a large fact table with a small dimension table. Broadcast variables are immutable and serialized for optimal network transfer, then deserialized on each node for fast in-memory access. They are especially valuable in Spark SQL queries and machine learning algorithms where reference data needs to be repeatedly accessed. For example, broadcasting a lookup table prevents Spark from repeatedly shuffling the same data across the network, leading to substantial performance gains. Developers create broadcast variables using Spark context.broadcast and access their values with .value, ensuring thread-safe operations. Unlike regular variables, broadcast variables are managed by Spark's memory-aware storage system, which can spill to disk if memory pressure occurs, though this is rare due to their typical use case with smaller datasets. By minimizing data movement, broadcast variables optimize distributed processing while maintaining the immutability required for reliable parallel execution. Question 12. How do you optimize Spark jobs? 1. Use caching and persistence, cache or persist intermediate results to avoid recomputation and speed up iterative algorithms, or reuse datasets. 2. Avoid wide transformations. Wide transformations like groupByKey and join cause costly data shuffles. Replace them with optimized versions like reduceByKey or map-side joins. 3. Tune the number of partitions. Adjust partition count based on data volume and cluster size to balance workload and reduce stragglers or underutilized executors. 4. Use efficient file formats. Example, Parquet. Parquet and ORC are columnar formats that support predicate pushdown and compression, reducing I/O and speeding up queries. 5. Use broadcast joins when appropriate. Broadcast small datasets to all executors to avoid expensive shuffles in large joins, especially when joining a large table with a small one. Question 13. What is data skew in Spark and how do you handle it? Data skew occurs when data is unevenly distributed across partitions, causing some tasks to process significantly more records than others. This imbalance leads to straggler tasks, where a few executors work much longer than the rest, degrading performance and wasting cluster resources. Skew commonly arises during operations like join, group by, or reduce by key, where certain keys dominate the dataset. There are few strategies to mitigate data skew. 1. Salting, key randomization. Append a random prefix-suffix to skewed keys to distribute load. 2. Adaptive query execution, AQE. Enable it to dynamically coalesce small partitions and optimize skew joins by splitting large partitions. 3. Broadcast join for skewed tables. If one table is small, force a broadcast join. 4. Custom partitioning. Use repartition or define a custom partitioner to evenly distribute skewed keys. 5. Filter and process skewed keys separately. 6. Increase shuffle partitions. Question 14. Difference between reduceByKey and groupByKey? In Apache Spark, both reduceByKey and groupByKey are transformation operations used with key-value pair RDDs, but they behave quite differently in terms of performance and execution. reduceByKey performs a local aggregation on each partition before shuffling the data across the network. This means that Spark combines values with the same key within each partition before sending data to other partitions. As a result, it significantly reduces the amount of data shuffled between nodes, making it more efficient and scalable, especially for large datasets. On the other hand, groupByKey shuffles all the values for a key across the network and then groups them together. It doesn't perform any local aggregation, which can lead to high memory consumption and network overhead if the key has a large number of associated values. This makes groupByKey less efficient and more prone to out-of-memory errors compared to reduceByKey. In summary, while both achieve similar outcomes in grouping data by keys, reduceByKey is generally preferred for aggregation tasks due to its performance optimization through local pre-aggregation and reduced shuffling. Question 15. What is a DAG in Spark? In Apache Spark, a DAG, directed acyclic graph, is a fundamental concept that represents the sequence of computation steps or stages in a Spark job. When a user writes a series of transformations, like map, filter, or flat map, on a dataset, Spark does not execute these operations immediately. Instead, it builds a logical execution plan in the form of a DAG. Each node in this DAG represents an RDD or data frame, and the edges represent the transformations applied. This approach allows Spark to analyze the entire job holistically, apply optimizations like pipelining transformations, and minimize shuffles, which are expensive operations in distributed systems. Once an action, such as collect or save as text file, is invoked, Spark's DAG scheduler breaks the job down into stages based on shuffle boundaries, then further into tasks which are distributed across the cluster. The DAG ensures fault tolerance, as Spark can recompute lost data using the lineage information embedded in the graph. This model enables Spark to be highly efficient and resilient in handling large-scale data processing. And that wraps up our deep dive into the most commonly asked Spark interview questions and answers. Whether you're preparing for your next big data role or just brushing up your skills, I hope this video gave you the clarity and confidence you need. If you found this helpful, don't forget to like the video, subscribe to the channel, and hit that notification bell so you never miss a new update on tech interviews, big data, and beyond. Got more questions? Or maybe an interview experience to share? Drop it in the comments below. I'd love to hear from you and continue the conversation. Until next time, keep learning, keep growing, and as always, stay curious. Electric light bulb. Thanks for watching.